Hi, my name is Vivian Lee. I am working at Northeastern University as a postdoctoral research associate. I awarded 2015 Arnold O. Bankman Postdoc Fellowship with my research project, Glioblastoma Endothelial Interaction in 3D Bioprinted Tumor Vasculature Tissue. Yes, I know, it's a long title with boring technical jargons, but I will walk you through it, explaining each word with a little bit of background knowledge. Glioblastoma, called GBM in short, is the most malignant form of brain tumor, frequently kills patients within an year of diagnosis. These tumor cells are highly invasive, so complete removal of these cells by surgical resection is almost impossible. Next, endothelial. Endothelial cell is a basic unit of blood vessel. Glioblastoma endothelial interaction. One of hallmarks of GBM is the high degree of blood vessel formation, and GBM also uses blood vessel as a guide for tumor migration. Interfering GBM invasion near blood vessels may add a new therapeutic direction to reduce tumor invasion and vascularization. Three-dimensional bioprinting is a technology that allows dispensing living cells in a desired 3D pattern. Jelly-like materials, called hydrogel, are commonly used as a scaffold material for this type of cell printing. Three-dimensional structure can be fabricated by layer deposition. Now we have just one more line from the title. Tumor vascular tissue. Tumor means GBM, vascular is same as endothelial. So tumor vascular tissue means a body tissue with GBM tumor and blood vessels. Then why do we need tumor vascular tissue? In the past, the cancer research and drug screening for cancer therapy have been focused on using animal models. Animal models are effective for validating drugs when the leading drug candidates have been identified. However, they are less effective for initial screening due to the cost as well as the difference between mice and human models. 3D tumor vasculature tissue model will help to understand the biology of tumor cell behavior around blood vessels, and it will allow high-throughput drug screening. I developed 3 types of tumor vascular models. Each of them represents different tumor environments. The first model is to see the interaction between large blood vessels and tumor core. Second model is for the interaction between tumor core and capillary. It is more similar to actual brain tissue condition than the first one. The third model has capillary with scattered tumor cells, representing residual tumor cells after surgical resection. In the first model, the embedded tumor cells aggressively invaded, and then there was a regression of tumor invasion after drug treatment. However, some of the tumor cells survived from the drug treatment and resumed tumor growth and invasion again. This is an indication that the tumor cells develop therapeutic resistance in this 3D tissue model, showing the potential of this model for drug testing. The second model with capillary and tumor core was also successfully constructed using 3D bioprinting. In this model, I tested 3 different types of GBM cells. U87MG is a traditional cell line. SD2 and SD3 cells are collected from 2 different glioblastoma patients. These 3 types of tumor cells showed different behavior in the model. U87 tumor triggered death of nearby endothelial cells. On the other hand, the patient-derived cells, SD2 and SD3, maintained the capillary network. SD2 presents spiky invasion pattern, whereas SD3 showed more contact and interaction between GBM and endothelial cells. Similar pattern of invasion and endothelial interaction was observed in the third model. And these results from the in vitro tissue corresponded with in vivo result from mouse model. This shows the potential of 3D printed model in investigating patient-specific tumor behaviors under various conditions, such as chemotherapy or radiation, and ultimately helping to tailor patient-specific treatment strategy. All of this work wouldn't be possible without the generous support from Bankman Foundation. Beckman Foundation not only supports my research but also provide me with a very supportive scientific community. I also really appreciate that I had a chance to learn Dr. Beckman's contribution to science and his legacy through the fellowship. One of my favorites from Dr. Beckman's rules of success is, only by taking risks do you make progress. I have been working in the interdisciplinary field, combining biology, mechanical engineering, electrical engineering, and computer science all together to create living body tissues. Combining two or more of very distinct areas has been always challenging and risky for me. Dr. Beckman invented pH meter, oxygen analyzer, and many other instruments by combining chemistry and electronics. His approaches were new and innovative, probably risky at the time. He also took a big risk to quit his academic career and built a business that made those instruments available for thousands of people to use. As a result, his inventions changed our world in the hands of many scientists and engineers in industry, research institutes, and hospitals. Dr. Beckman's story brings me courage and inspirations to pursue my career in the interdisciplinary field. Another memorable quote of Dr. Beckman is, "Hire the best people, then get out of their way." This phrase always reminds me to be passionate about people as well as their science and be respectful and trustful to people. I believe what I learned through Arnold Beckman Fellowship will prepare me to be a successful leader and innovator in science, engineering, and technology. I want to thank again to the Beckman Foundation's generous support of my research and academic career. I hope more of talented scientists and engineers join Beckman family and spread Dr. Beckman's legacy to inspire more people. Thank you.